Hello everyone, welcome to Chapter 9, Section 1. This chapter is over nuclear radiation, and we are going to discuss the natural radioactivity and what this is and how it is useful. Throughout the chapter you will see sections about how radiation is useful, also how it can be harmful. Most of your isotopes of elements up to the atomic number 19 have stable nuclei. So this means that they're not going to be susceptible to radiation. However, we do have, pretty much after the atomic number 19, the isotopes can be radioactive because they have an unstable nucleus, and so they're going to emit some sort of radiation. We're going to look at what these particles include to become more stable. So they're going to change the composition of their nucleus. Okay, this is very, very, very different from balancing equations in Chapter 5, okay, where we had the same number of atoms on each side, and they balanced, and there was no change in the nucleus. So this is where this chemistry is very different. This chemistry is also, radioactive isotopes are so useful. So those of you that are going into medicine or going into be nursing, to be nurses, in any hospital you go into, you're going to find radioactive materials. And most of the time, these are beneficial to patients, whether it's for thyroid issues or cancer or scanning images to see if, to find tumors and things of that nature, and so it is very useful. However, too much exposure and too much radiation can be very harmful. Okay, so as you read through, and I've pulled up and I've given you guys some extra materials to read under your handouts and extra practice. So be sure you read those and kind of get an idea of what this, what nuclear chemistry, what it's good for, and the things that you want to be cautious of as well. But a radioactive isotope basically is going to emit radiation to become more stable, and it's identified by the mass number of the isotope. Okay, and so if we look here, we've got magnesium with an isotope. A stable isotope of 24 is its mass number. So remember that top number here is the mass number. So we call this magnesium 24. If we look at iodine, the mass number of 127 for iodine is going to be the stable isotope of iodine. Okay, if you look here, you'll see that the 12, don't forget that this number here, this is the subscript, is the atomic number of magnesium. Okay, so don't forget that number just comes from the periodic table. And the same for iodine. So if you look at your periodic table, that 53 comes from the periodic table. That's how many protons iodine has. That's its atomic number. Okay, the radioactive forms of these are here. So we've got magnesium, who has a naturally occurring stable isotope, but it also has a radioactive form. Magnesium 23 and magnesium 27 are radioactive. We're going to talk about exactly what this means in a minute. Iodine, the radioactive form, is iodine 125, that's its mass number, and iodine 131. Okay, uranium does not have a stable isotope. A lot of your heavier elements, I believe even after bismuth, do not occur naturally stable, so they're going to be radioactive. And uranium has a radioactive isotope of 235 and of 238. Okay, this table you want to become very, very familiar with. We're going to go through and talk about each, but when radiation is emitted, so when these nuclei can emit radiation, they're going to emit particles, and they become a more stable atom when they emit the particles. And so they take the form of alpha particles, neutrons, beta particles, positrons, or gamma rays. These are the different types of nuclear radiation. These are going to be very important that you know the type of radiation, you know the symbol, you know the change, you know the mass number, the charge, and all of that for balancing equations. In the next section, we're going to be balancing these types of equations, and you're going to have to know these in order to be able to do so. Okay, alpha particle is the symbol alpha, and it actually looks just like a helium atom. So it's like emitting helium atoms. It has a mass number of 4 and a charge of 2. Okay, there's its mass number there. A beta particle is basically a neutron, and it changes to a proton. An electron is emitted, and so we look at it as really looking like an electron here. That's where that E comes from. So it's got 2 symbols, B or 0, -1, E. So it has a -1 charge. A positron is kind of opposite of a beta particle. It looks very similar to a proton. When a proton changes, it's going to change to a neutron, and a positron is emitted. And it's got a +1 and a 0 mass. So 0 mass, both of these have 0 mass and a 1 plus charge that comes here. Your gamma rays are actually the most penetrating, but they have no mass and no charge. Okay. A proton is going to look just like a proton here. We've got a 1 mass number and a 1 atomic number. Has a 1 plus charge. And a neutron looks just like it would in the previous sections. And it's got a 1 mass number and a 0 atomic number. And this would be like a neutron that's being emitted. So these are particles or radiation that's going to be emitted from an unstable atom to form one of these types of radiation. So an alpha particle, I'll go through all of these again. So here they are listed for you. Alpha looks like a helium atom. Beta looks like an electron. Positron has a positive electron, if you want to think of it that way. Gamma rays, they have no mass, no charge. And so if we were to give the name and the symbol for the following types of radiation, you're going to want to be sure that you can do this on your own. So alpha radiation, so we'll go ahead and go to the solutions here. You can pause if you want to try to do them yourself. But we can look at the name and the symbol. So alpha radiation, we know that we could also use the symbol. Go ahead and get my pen here. Also use the symbol alpha. Okay. Radiation with a mass number of 0 and an atomic number of +1. So this is going to be this here, which is going to be the positron. Radiation that represents high energy radiation released from the nucleus. This is going to be your gamma rays here. They have no charge and no mass. And they are very, very high energy. For alpha particles, when alpha particles are emitted, we're going to look at more and more reactions in the next section. A paper or clothing will protect you from alpha particles. So your alpha particles are going to be the least penetrating. For beta particles, they're going to be a little bit more, you're going to need a little bit more protection from this radiation, a lab coat or gloves. So these are more penetrating than the alpha. For gamma rays, these are the most penetrating, so that's where we got the high, they're very high energy. And you will need a lead shield or a thick concrete wall to protect you from the gamma rays. So you want to limit the time spent near any sort of radioactive source, obviously. Anytime that you increase your distance from that source, the penetration obviously levels down and slows down as the further away you are. So the further away from the source, the better. So you obviously do not want to be around radiation, even small things like microwaves and X-rays and MRIs, things like that. You always want to keep to a limit. However, they are useful, so they're very useful in medicine and technology right now. Okay, this is the table kind of showing you with a thickness, how you would need, how much protection and shielding you would need from the alpha, beta, and gamma particles. So radium is a typical alpha particle, carbon-14 is a typical source of a beta particle, and technetium is a typical source of gamma rays. And this is actually used for stress tests in the hospital. They use this, and so it has to be very, very limited and have to be very, very careful, but it is used in the hospital. Okay, so what type of radiation will be blocked by lead? Okay, so that's going to be our gamma, and B says paper and clothing, that's going to be our alpha. So if we look at the answers here, gamma and alpha. Alright, so in a nutshell, basically this chapter is a lot different from the other chapters, and so we have to kind of decide to pair it with the gases so that you guys can maybe, gases they act differently than our solids and liquids, as well as the nuclear chemistry, nuclear radiation is different as well. This could be a very important chapter for you guys that are going into being nurses, to understand what you're using. So if you work in the cardiac unit or anywhere where they've got radioactive materials, then you can actually understand what is going on. So we will pick up with the balancing of these equations in the next section. Thank you.